Open Comsol. Select 2D model. Select Fluid Flow, and then Laminar Flow. Then press Add. After that, select Heat Transfer, and then Heat Transfer in Fluids, and then again press Add. Select Study. So now choose stationary type of the calculation, and then press Done. Let's begin with parameters we'll be needing in the simulation. For that, go to Global Definitions Parameters. In the table, type in the name of the parameter and required value in the expression field. In square brackets, you can put the units for every number used. When all parameters are entered to the table, please check in the value column that all units are recognized correctly. The next step, let's go to geometry and define geometry that will be used in the simulation. For that, we add 4 rectangular areas, pipe, heater, sensor, and reference sensor. Let's define the area pipe. For that, we will use the parameter pipe width for the width of the area, for the width of the rectangular. And the base position also can be defined in respect to that constant. That means your model can be parametrically changed so the overall system is still behaves like a flow sensor. So not all the parameters, not all the components will be broken apart when a single parameter is changed. After you change parameters in the model, in the geometry section, press Build Selected, and then for the geometry build all. You see the parameters now in meters, but in the parameter table, we define them like in centimeters units. For correct representation, select the section geometry, length units, centimeters. Then press build all, and again build all for the whole for the all elements. Let's define the heater component. Width will be 0.0005 centimeters. Height the same. So basically it means half a millimeter, obviously. The position again can be defined using predefined parameters. And again, to see that everything is correct, select build, and you see the element is in the graphics component. Sensor component has got the same geometrical parameters, but the position is different. Again, press build all. Okay, let's check what's wrong. There's typo here. Okay, and again, build all. So we see the sensor now in the graphics. It's defined reference sensor. The same geometrical parameters. The same width, the same height, but position Y is different. So the geometry is defined. Let's add materials. For that, press Materials, add material from library. And then select the liquid you're required to model. For the reference model, I use water. And silicon for their sensor. The material can be selected from built-in materials. You see, there are many different types of silicon, but here I'm using the material from built-in library. And I do double click by left button to add the material to the materials of the tree of the model. Close library of materials. Select liquid. In this case, this is water. You see, when you add the first material, all components and the geometry by default is assigned to that material. It is not correct form in our case, so delete solid elements from the water material and add those by selecting and clicking left button from the geometry, from the graphics. You see, now the indices of the elements are attached to the material, to the solid material, in this case, silicon. In the model tree, select laminar flow. And in the selection window, only the components which are of liquid properties should be left here, because it doesn't make any sense to calculate laminar flow in solid objects. So delete elements, solid elements from the laminar flow model. After that, fluid properties component should have this set of parameters. The set of initial values should be like this. And the set of walls should look like this. It is before we select here inlet element and outlet. Let's tune inlet. For that, for the velocity of liquid, first of all, select this border. This will be our inlet. And select inlet constant defined before. After this, we can tune outlet component. For that, select bottom border of the pipe. Now it's time to set parameters for heat transfer and fluids component. First of all, change the thickness of the model. Here I'm using assumption that the model of 2 millimeters of thickness. In the heat transfer, all components in the geometry and in the graphics window should be selected and attached to heat transfer and fluids component. Modify fluid subcomponent of the heat transfer and fluids model. Here, it is important to link heat transfer model and laminar flow model. For that, in velocity field, select velocity field option. So the output of the laminar flow model will be used in heat transfer and fluids model. Let's check initial values. That will be the initial step, initial conditions of the calculation of temperature. Now we add subcomponent of solid elements. to heat transfer model and add all the sensors by single click by left button. The window should look like this after that. Now we let the system know the heat transfer and fluids component to know where what's the flow conditions, where is inflow and where is outflow. For that, we add the following corresponding components: inflow and outflow. For inflow, similarly, like for the laminar flow submodel, we select upper border, and for outflow, bottom border. In inflow component, it's possible to select temperature of the inflow liquid. For this case, I select 300 kelvins, but for individual case, select this liquid, this temperature, so your liquid is not boiling. Check the boiling point for your liquid and select the temperature well below the boiling point of your liquid. For example, for water, boiling point temperature is about 373 kelvins. I select 70, roughly 70 kelvins below that point. So you can also select 70, 40 kelvins below the boiling point. Let's define border conditions from point of view of temperature. Here I add temperature subcomponent and attach this wall of the pipe, and I select the temperature of the wall of the same temperature of inflow liquid. This is important because now we are doing stationary solver, and it is a kind of simplification of the model. If your model, without that, it's difficult to calculate stationary task, and this is just for minimizing of time. Now add heat source, volume heat source. And then here we use heater power constant, defined in global definitions. Our heater is this element between the two sensors. Select them. So it is attached to heat source component. Now we can build mesh. Let's select normal element size, press build all. You see the number of domains and elements after the mesh is applied. Now we can do the first calculation. For that, select stationary solver and then press compute. Here you can see convergence plot, and after that you can see the distribution of, after the calculation is done, you can see the distribution of the velocity in the pipe, distribution of pressure, hydraulic pressure, and distribution of temperature. You see the liquid in close proximity to the heater is heated up, and that causes the heat of the sensor. To quantify and get plots of changes of the parameters you're interested in, quite useful to use probes. Let's add 2 probes to the model. For that, go to Definitions, do right-click, then select Probes, Domain Probe. Let's give some name, Domain Probe Hot, and put variable name. In this case, dom1 hot, and then select the element you'd like to have here. I'm interested in measuring temperature of this element. So I select it. It's now attached to this domain. And now I should tell the system what parameter I'm interested in. For that, press this element in the corner and then select our heat transfer and fluids submodel, and then temperature and temperature in kelvins. Do left double click. You see the expression T is temperature and the units will be kelvins. Now we can select what type of temperature we'll get over this area of the selected area. Is it integration or summation over the nodes? And in this case, I'm interested in integration. So that will be average integrated temperature over this element. Let's add the second probe. For that, we'll do the same. First of all, let's clear up the selection window and select this area. So that will be the second probe. And again, select heat transfer and fluids and temperature, and then temperature. Method of integration the same. Now select stationary solver and repeat computation. You see, probe plot appeared in this group of plots, and you see 2 dots corresponding to our probes. And also in the results, now you see probe plot with the table, which can be then used for the export of the parameters you are retrieving by those 2 probes. Let's fix a little bit our probe 2. For that, let's give some name, domain probe code. Just not to forget what we're measuring here. To study how our temperatures for the probe 1 and the probe 2, when the flow, inlet flow changes, it's useful to use the following component. Select stationary in the study, and then select study and add parametric sweep. Parametric sweep allows you to change any parameter defined in global definitions here. So from this table, in a way you'd like to. To add parameter, select add, and then select the parameter you'd like to change. Here we're interested in inlet flow. In parameter value list, it's possible to just put the set of numbers, but also it's useful to use range. Select here range, and you can say the initial value of the flow. Because we're doing stationary calculations, if we select initial flow of 0, your stationary task won't be successfully calculated. So for that to have some reasonable time for the stationary task to be calculated, select here some absolute minor flow, but not 0. I use step 0.02 millimeters per second, and the stop 0.2 millimeters per second. Add. Select parameter unit millimeters per second. Probably it's better to put here 5, because it's already tested for me. So then, also during the parametric sweep calculation, when we press compute, we can select plot to be plotted and to interactively see what's going on. For that, select our probe plot with 2 probes defined before. And select manual probes. Yeah, our 2 probes. Here we select the accumulated probe table, so the output values calculated will be stored in the table. Let's have new table. And everything else is okay. Let's press compute and see what's going on with the probe plot. You see the interactive change of the temperatures calculated for different values of inlet flow defined by you in the parametric sweep. When the inlet flow is about 0, there is absolute minor difference between the 2 sensors attached to the pipe. But with the increase of inlet flow, the difference increases, but both temperatures behave non-linearly with the change of inlet flow. Now to use in our calculations, let's add export. Do right-click, select export plot, and here in the settings of the export for the plot, select our probe our plot with 2 probes. Select file text like text, file type text, and then you can select file to be exported like a TXT file. Data formats, I'd prefer to use spreadsheet, so the data can be exported to Excel. Yes, and now you can press export. Let's check. You see this file data with the first column, it is inlet flow in millimeters per second. The second column is the domain probe hot, and the third, domain probe cold. Let's export the data to Excel. Select Excel file, Excel software. New table, then data. Yes, let's save. The work spreadsheet. Now select get from txt CSV. Select the file data with your data. Select delimiter, custom, you see preview, and then press load. Let's plot change of hot probe and cold probe. Select columns and then insert and select chart. Yes, so not too beautiful. Let's repeat. Select data. We can press shift, then repeat, insert. Oh, the same. Yes, that is because we have to replace dot with comma. Replace all. Now those are numerical values. Again, repeat, selection, insert, chart, and type. So you see the change of the hot temperature, hot sensor temperature. Now let's plot the cold one. Okay. And the linearity isn't good, right? But if we select the average temperature, the linearity should be much improved. Simple averaging. Let's look at the plot. This should be excluded. So it's pretty much linear. So that's your function of change of temperature you have to optimize and to satisfy the requirements of nonlinearity. So that is the basics of the Comsol you have to use in the modeling to build your model. But of course, you can start from the reference model I uploaded to Moodle. Thank you for your attention.